And we're back. Welcome back from the weekend. Today we'll continue on with our discussion of feature selection, specifically PCA. Before we do so, the reading for this module on PCA is tutorial on principal component analysis. There is the URL. Please make sure you're keeping up with the reading. I will be releasing an assignment, project number 1, this evening, being Tuesday, September 15th. When we last left off, we talked about this transformation of our data in a new coordinate system. And as such, we said that matrix Y is equal to matrix P times matrix X. And it just so happens that the rows of our system P behave like the new basis for all of the points that are originally in representation X. And so where we left off last, we talked about each term in YI, the ith column of the Y matrix, is the result of taking the dot product of each of the rows of P, the bases, with each column of our design matrix, each measurement. And so each one of these columns in the new representation Y is a projection of the ith column of X onto the jth row of P. And so the Yi is the value of all of these projections of each data point from our original design matrix in our X representation into this new basis described by the rows of P. Okay, so let's take a look at the PCA approach. So what's happening here? The rows of P form a new basis vector, set of basis vectors for our existing data X. And at the outset, we said PCA assumes linearity, right? This linearity makes it easy to find the new basis function. This new basis function is a linear combination of the bases in our original X space representation. The row vectors of P will become the principal components then of our new representation Y, and the PCA problem is now to set out to find exactly what a good linear transformation P is. And so when we talk about good expression, remember that we want these three things. We want to reduce noise, we want to introduce a rotation, because with the rotation, we can align the axes, or the principal components of P, with the true dynamics of the system. And we also want to eliminate redundancy, because two axes or two features in our original representation might be saying the same thing. We don't need multiple copies of features saying the same thing. And so let's look at noise and rotation. Now, noise in general is measured on no absolute scale. You can measure a signal-to-noise ratio, and the signal-to-noise ratio is nothing more than the proportion of the variance of your signal, your dynamics, in this case, our motion in that x-hat direction of the mass in the spring mass damper system, divided by the variance of the noise. And when the signal-to-noise ratio is greater than, much greater than 1, we have so-called precision data. Our dynamics are not adulterated to a large degree by noise. But when this signal-to-noise ratio, if it's small, that means we have highly contaminated data. It's confounded by noise. And so let's take a look at an example. Here we have a coordinate system in original representation, and it's defined by two coordinate axes. We have, and I'll select my pen color here, we have our X direction, and we have our Y direction. And let's imagine these are from the perspective of camera A. Now, in this figure, I've drawn some points. And these points, let's just imagine these are positions of that mass as it has been traveling in a straight line, or close to a straight line. Now, let's assume that our camera A in this case, can measure the motion, and that motion occurs on a straight line. And therefore, any deviation in the motion of the camera from the straight line is certainly noise. And so here, as we can see, well, sometimes that mass travels in a straight line. And here's a point, Here's a point. Here's a point. Sometimes it deviates. Sometimes it deviates a little bit from a straight line. Sometimes it deviates, like in this case, it deviates a lot from traveling in a straight line. And so in essence, our mass is traveling in this direction and then in the other direction given by these data points. And so if we looked at the variance associated with this axis and the variance associated with the other axis, we can see that the principal or the primary variance, that's our signal, and the secondary variance for the other axis, orthogonal, that's going to be our noise. And so the ratio of these two lines, this line representing that component of motion, and that line representing the other component of motion, the variance in position associated with each one of these directions, that's going to be our signal and our noise. Okay. And so one of the key assumptions that we're going to make in this is that the largest variance are going to describe the dynamics of interest. And this makes sense if you think about it in the case of a spring. So let's imagine here we had a spring, and let me just kind of draw these coordinate axes, and we said that was XA and that's YA. And let's say we have the connection point, and we have the spring, and then we have the mass here. And when you displace this mass, it's going to oscillate. Sometimes it's going to oscillate straight down, straight back. Other times it's going to pull to one side, or maybe pull to the other side, or pull down here, for example. Now, it's a really strange spring. Let's imagine that the dynamics were such that the largest direction of variance was not the dynamics of interest. So that would mean you would take the spring and you displace it some amount delta x, but instead of moving delta x in this direction or close to delta x plus or minus some other variance in the noise direction, imagine if you displace it delta x and that spring, instead of oscillating forward and backwards, imagine if that spring, when you displace it delta x, it's going to start going this way, in this direction, plus and minus. That's a really weird spring. You displace it delta x, and it displaces delta x going side to side, and a very small amount going forward and backwards. That'd be a really strange spring. So this is our key assumption, that the direction of variance that is largest, that's going to be the dynamics of interest, because we never have a spring that behaves this way. That would be just plain weird. Okay. So the native basis of what we observe, that's our x, right? That would be represented by this coordinate frame, which is XA and YA, this particular coordinate frame corresponding to the measurement instrument. And so the idea then, when we're finding this P, is we want to find the rotation such that we can align with the largest variance. And how do we do that? Well, what happens if we rotate this coordinate axis the following way, that way, anti-clockwise? If we do that, well, we can rotate it such that the axes, and I'll draw it in its rotated position, are the following, where this is the new YA, call that YA prime, and this is the new XA, let's call that XA prime. Now, if we rotate that with linear system P, our optimal rotation, now we can align this XA axis with the direction of largest variance. And we can see here the direction of largest variance is at this 45-degree angle is drawn in this particular figure. And so the idea then is determining what type of rotation for this linear transformation P, this change of basis, gives us the direction of best fit to the direction of greatest variance, which is the direction associated with the dynamics of interest. And as such, this YA direction is then the direction associated with the noise. Okay. And so let's take a look at the second point, our redundancy. We have multiple cameras that are recording the system dynamics. And the question that we ask when we think about redundancy is, do we need all of these measurements, the XA, YA, the XB, YB, the XC, YC, for each of these three cameras? So let's assume we have different measurement types. We'll call them R1, and let's assume R1 is associated with the horizontal axis in each case, and R2 is the measurement type or feature that is associated with the vertical axis. And so if we look at this setup here, we have three different situations. One in frame A for low redundancy, B for medium redundancy, and C for high redundancy. And what redundancy tells us is if we can predict measurement type R1, one of the measurement types, based on the other. If that we can, that means they're statistically dependent. Conversely, if we cannot predict R1 from R2 or R2 from R1, then they're statistically independent. For example, the position of the camera along XA has no bearing on the humidity in the room. They have nothing to do with one another, therefore independent. Now, in frame A is an example of low redundancy. Let's go along R1 direction for that measurement. If we increase R1 from this point and take a unit step to the next point, we see that R2 has some decrease, right? R2 decreases from that higher value to this lower value. So we have a change in R1, a unit step increase. We have a unit step decrease commensurately, or some amount of decrease in R2. But then again, if we take another step in R1 from this point to that point, well, we have an increase in R1, but for that similar unit step increase in R1, we have, instead of a decrease in R2, we have an increase in R2 that's about the same. So there's not a direct relationship or coupling, if you will, between a unit step increase in R1, delta R1, and a unit step increase in delta R2. It's not consistent. Sometimes it decreases when R2 decreases when R1 increases. Sometimes R2 increases when R1 increases. Likewise, sometimes that increase is different. If we go from, say, here to here, we notice R1, change in R1 is very small, but the change in R2 is relatively large. So there is no dependence or very small dependence, unit step increase in R1 causing a unit step increase in R2 or being associated. So that particular example describes this idea of independence statistically, or this low redundancy, because they're saying entirely different things. There's no information coupling between the values in R1 and R2, these two measurement types. So let's take a look at this idea of medium redundancy, right in the middle. There's a relationship, but it's not terribly strong. Again, if we look at a unit step increase in R1, this is delta R1, we get a unit step decrease in R2. We get a delta R2. If we go over here, well, we see a unit step increase in R1. Well, there's still a unit step increase in R2, but it's not quite as big as it was before, and it's an increase and not a decrease. Well, we have here a unit step increase in R1 is a decrease in R2, okay. Here we see a unit step increase in R1 is a unit step decrease in R2. So there seems like a relationship. There's increase in R1 is decrease in R2, increase in R1 again is a decrease in R2, increase in R1 again is a decrease in R2. But we also have here, well, that's kind of like a little bit of a violation of that. We have an increase in R1 leads to an increase in R2. So we have a relationship, but it's not strong. Some of the times that relationship persists, but not all the time that relationship persists. Okay, so that's medium redundancy. So let's look at this last concept of high redundancy, an example. Again, we have R1, measurement type R1, and measurement type R2. In this case, they're highly correlated. And notice for every single example, for a unit step increase in R1, there's a unit step decrease in R2. So we have an increase in R1, decrease in R2. We have an increase in R1, a decrease in R2. And that persists everywhere along this line, plus or minus small deltas, but nonetheless, this persists. An example of this is in highly correlated measurements that you might get if you have two cameras. So let's say if you have camera A, and very close by you have camera B. Now, if you have that case, well, the coordinate system for camera A and the coordinate system for camera B, if you're viewing the same motion for your spring mass damper system, well, they're both going to see something very similar in terms of the motion path. This one is going to see a path that way, and this one, its path that it measures might be a little bit different, but it's going to be very much similar, and you're going to get a situation that looks like this plot here in frame C. And so this is high redundancy, and in the case of high redundancy, you don't need both XA, YA, as well as XB, YB. You can get away with just one of them. You don't need these redundant measurements because they're talking about the same thing. So you don't need both of these recordings. So that's an example of high redundancy. So one of the things we're going to use, or tools, to talk about this redundancy is this idea of high covariance. And covariance is a linear relationship that describes this idea of a unit step increase or decrease in one measurement is associated with a unit step increase or decrease in another measurement. So let's talk about covariance for the two variable case. And what we do for the two variable case, we take the best fit line for the data and we calculate that line slope. So here in the previous frame, you'll notice we have our best fit line here, low redundancy, medium redundancy, and high redundancy, and we're just calculating the slope. Okay, and that slope gives you a notion of this degree of coupling between the different measurement types. But what do you do when you have higher dimensionality? So let's take a look at this. Suppose you have a bunch of measurements, n many measurements. We'll call that measurement system A, and we have measurement system B. The mean, we can assume, of measurement system A, mu A, is 0. Likewise, for B, mu B is also 0. And that's a typo. That should be a B. So the variance of A, well, we're just going to compute it using this angle bracket notation, is just sigma squared A. And variance of measurement type B is sigma squared B. So this covariance is the degree of linear relationship, and that linear is important, that linear relationship between two variables. If covariance is small, that means you have low redundancy. It means that on average, unit step increase for one or decrease for one variable does not cause much of a unit step increase or decrease for the other variable. If covariance is high, that means you have a high degree of redundancy. They're coupled. A unit step increase or decrease for one is causing a non-zero unit step increase or decrease for another, and that's consistent. All right. So that means in the first case, low redundancy, we have small covariance. In the second case, we'd say that has medium covariance. And then lastly, in the third case, that would be a large covariance. And so the covariance between two measurement types, A and B, sigma squared AB, is going to be at least 0, greater than or equal to 0, where equality is reached if A and B are uncorrelated. And of course, if you have a measurement type with itself, well, that's just the variance. So let's assume we have two column vectors for our two measurement types, A and B. So these are our n measurements for measurement type A, and our n measurements in time for measurement type B. So if we want to compute centered about origin, so it's normalized, the mean is 0. If we want to compute the covariance between measurement type A and B, that's just 1 upon n minus 1 times AB transpose. Now, you can try this out in MATLAB. That is not the inner product. That is the outer product. And if we take A1, A2, up through AN, and we multiply that times B transpose, well, if we take B transpose, that's just a row vector. That's B1, B2, up through including Bn. Now, by the rules of matrix multiplication, you take A1 times B1, that's A1 times B1, you have A1 times B2, A1 times B2, etc., A1 times Bn. And then you take A2 times B1, etc., A2 times Bn. And lastly, you take An times B1, etc., up to A1 times Bn. And if you do that outer product between these two vectors, okay, well, you end up with a matrix. And that matrix, when we take the multiply it by that scalar 1 over n minus 1, that is our covariance. So that's not a mistake to say AB transpose. And I encourage you, try this in MATLAB to convince yourself that this works. Or conversely, if A and B are row vectors, you could produce this by A transpose B, which is just the same as taking this quantity and taking the transpose of that. Okay. So this is the outer product. The covariance is nothing more than what looks like almost like an average of the outer products. So it's the scaled outer product, where the vectors are the measurement types, where each one of these, this indexes over a measurement taken in time in our example. Okay. And so let's define a data set as a set of row vectors in time. And so each measurement type is going to occupy a row. And so here we have the first measurement type, we have the second measurement type, up to the mth measurement type. Now, each one of these measurement types are what we were calling features. All right, so in this particular column, we're going to have the first measurement across each of the m features. But we're going to take a single feature, and each row here represents a single feature, where the column is the sample in time. So here, the rows, these are the features, and I'm calling the features a measurement type. So in this particular case, if we take n samples over time for m measurement types or features, this is going to be an m by n design matrix. But remember, it's a little different from the data set. Here, we're talking about features along the rows, not samples, not feature vectors. Okay. So now, if we were to compute the covariance matrix, well, the covariance matrix of this system is just 1 over n minus 1, x outer product with itself, so x transpose. So we can do this outer product between sets of vectors, not just individual vectors. Okay, so in this particular case, if we do this outer product between this linear system with itself, each result we get for the ith row, ith column of the resulting covariance matrix is nothing more than the dot product between the ith vector and the jth vector. So if we look at this a little differently, well, we have x, we have x1, our measurement type of the first type, x2, our measurement type of the second type, through xm, our last measurement type. Okay, so if we take the transpose, that means we have x1, x2, so our measurement types are along the columns instead of the rows, up to and including xm. So now, by the rules of matrix multiplication, so that means we have a result here for the covariance, 1 over n minus 1. Okay, so we take this one times that. that's x1 dot x1. This one times that's x1 dotted with x2, and so forth, x1 dotted with xm. And then lastly, down here, we have xm dotted with x1 through xm dotted with xm. So these entries are the product between all pairs of vectors, where the vectors here, these n vectors, the rows of this special design matrix, are the measurement types. All of the values a single feature takes on throughout n many different measurements. Okay, so an observation about this covariance matrix, well, it's a square matrix, because if we take x, which is m by n, and we multiply that times x transpose, which is n by m, well, the resulting covariance of x, is going to be of rank m by m. So it is a square matrix, and it is symmetric, right? If we look at this is x1 times xm. This is xm times x1. Dot product is commutative, so it is going to be symmetric about the diagonal. So it is a square matrix, and it's symmetric. And moreover, the diagonal, if we look at it, it's x1 dotted with x1, x2 dotted with x2, and so forth up to xm dotted with xm. These are the variances of the measurement types centered about the origin. And this is a square matrix of rank m by m, so it's square and it's symmetric. The off-diagonal components, those are going to be the covariances between the measurement types. We have xi dotted with xj, well, that's a covariance. Okay. And so here, this covariance matrix convince you it's the scaled outer product between these systems, these special design matrix over measurement types or features in time, and it's nothing more than the outer product between systems of measurement types. The diagonal elements of this matrix these are the variances, and the off-diagonal components of this matrix, these are the covariances. Okay. So now, the large terms we said, we want the interesting dynamics to be the variance that are largest. And we said this idea of covariance can be used to measure redundancy. So what we want then is to have our large terms along the diagonals, i.e. the variances should be large, and then the covariances off diagonal should be small because we want low redundancy. That's what we're after when we're trying to identify the interesting dynamics. And we're trying to find this linear system that reduces noise, off diagonal covariance is small, and identifies the signal. The on diagonal terms, so variances, are large, and the largest variance, we'll make the assumption, as we said before, are the interesting dynamics. So essentially what we want to do, we said y is equal to px, and p was our transformation. Now certainly in its original form, this has a covariance. We call that cx, and in the transformed version, well, that data also has a covariance. We're going to call that cy. Now, ideally, what we want P to do is to manipulate the covariance matrix associated with our original input features, our measurements, such that the covariance of the resulting system minimizes redundancy, i.e. makes the off-diagonal terms low. How low can you make it? 0 is the lowest you can make it, while also maximizing the signal-to-noise ratio, where you're measuring that by the variance. And so essentially, because our covariance is minimum at 0, that means that the best P you can select is one that produces a Y whose covariance is large in its diagonal terms and 0 in its off-diagonal terms. So what does that mean? That means we want the diagonal matrix. A diagonal matrix is a matrix of the form exactly as we described. The diagonal components are non-zero, and in this case, we want them to be large, and the off-diagonal components, covariances, are all zero. So we essentially want a P that when we transform our original representation, the result is that the associated covariance matrix, CY, is diagonalized. Okay, so let's take a look at this a little bit more mathematically. We said P is going to be treated as a set of basis vectors. And this P matrix, P, we said consisted of a set of rows, P1 through Pm. And these rows are vectors, and these vectors are going to be the basis of our original linear system, X. Okay. So we have M measurement types for X, and we had N many samples, Xn, and we had N columns, that's the number of samples, and we had M rows, that's the number of features. Okay, so essentially what we're doing is we have a system P, and the rows of P are going to be basis vectors. So let's further describe this P here. So all of the basis vectors, regardless of their value, we're going to assume they have the property that they're orthogonal. And what that means is that if we take the dot product with between any two vectors from this P system, well, they're going to be zero unless you take Pi dotted with Pi. It's a delta function. And so, moreover, P is going to be an orthonormal matrix. And for this orthonormal matrix, the directions with the largest variance, not all of them, but those that have the largest variance, are going to represent the direction in which your signal occurs. And these are going to be the most important or the principal basis vectors describing the dynamics of interest. So what does this P do? P is going to rotate your axes such that some principal axis or some set of axes are going to align maximally with the axis in the original system along which the variance is maximized. And that's exactly what Pca is doing. So essentially what you do in Pca, you're going to take this cloud of measurements, you're going to shift the axis XA and YA so that this cloud is centered at origin. Okay, so it's going to be centered at origin. And then you're going to rotate your axes, and that's your transformation P, such that it's aligned with XA, YA. So it's aligned with XA, YA. And the linear transformation that does that, P, is going to diagonalize our covariance matrix. Okay. Now, in some descriptions, they explain it this way. They have the original measurement system. You have your axes. You have your YA. You have your XA. And you take your YA and XA, you shift them to origin. So here's XA prime. Here's YA prime. And then you rotate it. Here's YA double prime. And here's XA double prime. So what this P is doing, it's doing this rotation to align its axes in the direction of highest variance, eliminating redundancy. So you start out in this algorithm, Pca, you select the normalized direction in your m-dimensional space along which the variance of your observations is maximized. You're going to call this your first principal component. Then you're going to find another direction orthogonal to the first one along which the variance is maximized. And you keep doing this again and again until you have m vectors, and these are your so-called principal components. Now, certainly there are ways to find orthonormal vectors through things like Gram-Schmidt orthogonalization. That's one way you can find a set of orthonormal vectors. But let's look at what the Pca approach does. What the Pca approach does is it finds a P based on the eigenvectors of your covariance matrix. So you want to find a P such that y equals Px, and you want to find such a P such that the covariance of the resulting representation y is diagonalized. It has a diagonalized form. Well, one way of doing diagonalization is using the Eigen Decomposition. So we can assume that the rows of P are the principal components of the X, okay? And let's write an expression for the covariance of the resulting linear system Y. That's the new representation. So the covariance of system Y is just the scaled outer product of Y, that new representation. That's Y transpose, okay? So now we're going to make a substitution for what Y is. Y is just Px. It's that linear transformation on X. So we're going to substitute for Y at Px here. We're going to substitute for Y in the Y transpose of Px here. So now we're going to do this transpose operation. Well, Px transpose is nothing more than X transpose P transpose. So we have that multiplied by Px. We have Px, X transpose, P transpose. We can collect terms together. So here we can take this XX transpose and we could perform this multiplication first. We can associate that multiplication. Associative rule allows us to do that. So now we have Px, X transpose, P transpose. Okay. So we can associate this XX transpose, and we know that's a square matrix, and square matrix is also invertible. So let's redefine that XX transpose. Let's just give it a new name. Let's call that result A. And A is going to be symmetric, right? So we know it's going to be symmetric because X is just our original data matrix, and X was M by N. And so we're going to have M by N times N by M. That's just an M by M matrix, which is square. And it is also symmetric. The outer product is result is symmetric. Okay, so now we have our new version of the system, and we're going to call this P transpose. That's just the substitution we're substituting here for the XX transpose. We're calling that A. So A is symmetric. So this is our new version of our covariance for Y. We've made that substitution, and we've grouped together terms, associative rule, multiplication. And now we're going to say, okay, well, what form does A take in order for this covariance to be diagonalized? Well, for A to be diagonalized, well, it's of the form informed by the Eigen Decomposition. So we have our matrix of eigenvectors, we have its transpose times a diagonal matrix. That's what it means to diagonalize. The Eigen Decomposition diagonalizes a linear system. So we have our Eigen Decomposition, and A has some number of rows, which are the orthonormal eigenvectors, the number of rows here. So we can, if the rank of A is less than M, then the data that we have originally from X is going to be in some subspace, a reduced dimension from the original M dimensions for our measurements. And so one of the things we can do is fill in our matrix of eigenvectors with our orthonormal basis vectors of a rank such that A's rank is less than our original dimensionality. So not only can we diagonalize, we can also reduce the dimension with this Pca approach. So each row of our P transformation will treat this as an eigenvector of XX transpose. And so if P is the transpose of eigenvector, and let's just set that value, we can now substitute into what we had for this PAP. So A is going to be diagonalized. A is decomposed in the following way. It's just a diagonalized form given rise to by the Eigen Decomposition. And we're going to make the assumption that P is an eigenvector of our X transpose. Because remember, P is going to change the original basis. It's a linear combination of the basis vectors that give you your measurement data in this representation X. And so if P is a linear combination, well, one such linear combination, well, is arrived upon by eigenvectors. So let's assume that this P is an eigenvector of our original representation, the covariance of XX transpose. And so P is E T transpose, okay. Now, if we substitute in, we're going to substitute this into this A is diagonalized. So we have A in diagonalized form, and P is an eigenvector of this data representation. We can now substitute in this P for our eigenvectors that diagonalize A. Okay, so let's take a look at this. So if that's the case, if P is equal to E transpose, well, to diagonalize A, we have E, the diagonal matrix, times E transpose, this matrix of the where E is the matrix of eigenvectors, it's the row matrix, and its transpose, and D is just the diagonal. We have terms on diagonal that are non-zero and off diagonal that are zero. It's this diagonal form for this linear system A. Okay, so if P is the Eigen Decomposition, the eigenvectors of XX transpose, remember, when we pose this matrix D, we said we're going to take our A, and A is going to be XX transpose. We said that A is diagonalized by this XX transpose diagonalized in this form using the Eigen Decomposition. And so if we treat P as the eigenvectors of our XX transpose, well, we can substitute this P here for this E because P will diagonalize our XX transpose. All right. So we substitute this expression for P as our row matrix of eigenvectors, and we put in a P transpose here because P is E transpose. To get E, we write P transpose. So now we have P transpose D times P is our new expression for A. And just to remind you, A is this diagonalized form of our X transpose, right? So we can write it as XX transpose, or we can write it as a diagonalized form. And we're just saying now that P is going to be that eigenvector of the original data that we had, because it's a change of basis, and an eigenvector is orthonormal basis, and we can use that to change our basis. So we substitute in this P, we get P transpose D times P, and because we have an orthogonal matrix P, right, if it's a matrix of orthogonal basis vectors, which it is if it's a set of eigenvectors, the inverse is equal to the transpose. And that's just linear algebraic property of what it means to be an orthogonal matrix. So P's inverse is its transpose, and its transpose is its inverse. So that being the case, now let's pose our covariance matrix. So we're going to take our covariance matrix, and we have P times AP. Our covariance matrix Y is just P, XX transpose, P transpose, right? That's what we started out with, because we did the substitution of Y equals PX. We grouped together the X's, and we called this expression A. So we start out with a covariance matrix as PA, P transpose. So now we're going to take A, and we're going to substitute the diagonal form of A, right? So instead of XX transpose, we're going to substitute in the Eigen Decomposition version, which we wrote down as P transpose DP. And we assume that P is the eigenvector for XX transpose, for the covariance of X. So we take this PAP, we substitute for what A is, so that gives us P, A, P transpose. We substitute in for A, that P transpose D, P. We have that P and P transpose. Okay, so now what we're left with, we associate the leading P, P transpose, and we associate this multiplication of the trailing P, P transpose. So we have this equivalent expression for the covariance of the resulting system Y. We have P, P transpose, D, P, P transpose. So we use this fact that the transpose is the inverse and the inverse is the transpose. Well, here's a transpose. We rewrite it as P inverse. Here's a transpose. We rewrite that as P inverse. So now we have 1 upon n minus 1, P, P inverse, quantity, D, quantity, P, P inverse. Well, you multiply some linear system by its inverse. That's just the identity. So we have identity matrix here. We have identity matrix here. And now what we're left with is 1 upon n minus 1 times this diagonal matrix. And lo and behold, the covariance of the resulting transformed version of the data is linearized. It's diagonalized. And so in choosing this P matrix to be a row matrix of eigenvectors of the original system X, X transpose, by choosing that, making that choice, we diagonalize the covariance matrix of the Y system. Okay, so what does that say? It says, in order to choose the appropriate P, we have to set the rows of P to be the eigenvectors that diagonalize this covariance matrix in the new representation. So what do we have? We have that the principal components of our original representation are the eigenvectors of XX transpose, and these choices are the rows that we're going to use for P in order to get a diagonalized covariance matrix for the targeted system. So we take the outer product, which is your scaled covariance of the original representation, and the transformation we're going to apply are the eigenvectors. And that's going to be the rows of our P matrix, that transformation to the new representation. The ith diagonal value of that covariance matrix of the transformed system is going to be the variance of X, our original representation, in the Pi direction. And so that ith position is going to be the variance in direction Pi, which is that ith row of our linear system P. And so PCA of some representation X assumes that you're going to center your data. That means you're going to subtract the mean of each measurement type, and then you compute the eigenvectors of XX transpose for that centered data, and then you use the eigenvectors that you get as a result of the Eigen Decomposition, that diagonalizing of this covariance matrix in X system, as your P matrix. And those are just the eigenvectors P1 up through PM. Okay, so with that, that's what PCA is doing, and it's a general tool you can use for feature selection, because if you only employ a subset of the original M vectors, then your resulting Y representation is going to have a lower dimension. So rather than projecting over all the P, you might project over maybe some Q, many vectors, where Q necessarily, Q is less than M. And so your resulting Y representation is going to be of lower rank than the original representation M. And you can think of principal component analysis as a type of feature selection where the features in the new representation are a linear combination, some synthesis from the features of the original representation. And just by its properties of doing this rotation and this alignment, your representing the principal dynamics, reducing redundancy in addition to maximizing your signal-to-noise ratio. Okay, so with that, that's all I had for today. Next time, we'll continue on with more feature selection, looking at other methods. But PCA is a really important tool in your toolbox for reducing noise, amplifying your signal, finding important dynamics, while also synthesizing a new representation that can reduce that dimensionality for you. Now, PCA doesn't work for everything. It makes the presumption that you're going to have a linear change. And so if your data is not well served by linear representations, PCA will not do well for you. But if your data is well suited for linear transformation, then PCA will work quite well for you. So with that, we'll end there. And as usual, please stay healthy, stay safe, and I will see you all on Thursday.